So gradients. A gradient is an operator that we can apply to a surface. It's a type of derivative, it's a type of multivariable derivative, type of generalization. One way that you can generalize the regular derivative. Um, and here, what is our notion of gradient? It's the vector containing the partial derivatives of a surface. How would you write that? So that's saying in words. Math notation. So it's written with this symbol for the gradient, right? And then if you write that out, what is there in the vector? It's partial x and partial y, right? So it's in the same order that the variables appear, you put those partial derivatives, right? So partial x, then partial y. If you had, in 3D, if you had so this would be the gradient of a, two variable surface, right? But say you had a function with three inputs, you could keep going, right? df, dx, df, dy, df, dz, right? And so on, right? So however many variables you have, you just take that many partials, stack them in a vector. That's the gradient, right? Okay, so that's what it is and how to calculate it. But how to picture it? What does it look like? What does it do, right? Well, there's a big theorem, and so we'll state the theorem and then we'll justify it. Um, the gradient of a surface gives the direction of steepest ascent. Right? This is a really important fact about gradients, and actually just a really important fact in mathematics and computer science in general. So this is what the gradient does geometrically. And here I'm going to demonstrate this and kind of justify it in the case where the surface has just two inputs. It still works if the surface has more, but it's by far easiest to picture if the surface has just x and y as inputs, right? So let's look at this in a diagram, right? What on earth is happening? So look at a some generic surface, right? And look and think about its graph. Right? So here's x, y, and z. And then we have the graph of some surface here floating up above the xy plane, right? And then what we're saying is we have, whatever our favorite point is on the surface, right? So say this point here. And, there's there's the xy that correspond to that point x, so here's some xy. And then up here is some, point x, y, f of xy. Right, that formula gives us the z-coordinate of the surface. And then we want to find the direction of steepest descent, right? So in this case, it kind of, the way I have it drawn, it kind of looks like this seems to be like down here, downhill this way. Maybe it's flat along this line. Maybe it's slightly uphill this way. Maybe it's most uphill this way, right? And most downhill that way, something like that, right? So and here I don't have we'll do a concrete one in a second. Here I don't have a concrete one, I just have a general one. But so what's the idea there? Um, the idea is all of the rates of ascent or descent from that point are completely determined by the tangent plane, right? If you can solve this problem for planes, then you've solved it for a general surface, because once you solve it for a plane, then just take your surface and approximate it by the tangent plane at that point, And then the rate of steepest descent in the tangent plane will be the rate of steepest descent for the surface, or the direction of steepest descent for the tangent plane will be the direction of steepest descent for the surface, right? Um, so that's the key idea here is we'll just solve this problem for the tangent plane instead, right? So this is one of these lovely cases where you can take your surface and throw it away and replace it with the tangent line and solve that, or sorry, tangent plane. In Calc 1, sometimes you replace it with the tangent line, right? But you know, to take your surface, throw it away, replace it with the tangent plane, and solve it for that simpler object instead, right? So that's the nice thing that all we have to do is solve this for the case of a tangent plane, and we've solved it in general, right? Um, so let's do this now. So now consider the tangent plane. And what does the tangent plane look like? It looks like the z coordinate, right? And let's give these specific names just so that we can have x and y still represent variables. So let's call this point A, B, where we take the tangent plane, right? So I have f of A, f of B as the z coordinate. Um, so let's call this tangent plane. It starts at this z coordinate, right? And then what does it do from there? It does the um, rate of change in the x direction times the delta x, the change in x, right? And then similarly for y, right? This is how we build our tangent plane. So there's the tangent plane. And then what I want to do is I want to think about um, in this tangent plane, I want to think about what the level curves are in this tangent plane. So let's do that. Let's find I want to find the level curves for this tangent plane. Z equals, Z equals, Z equals, right? So let's find the level curves, right? So if I pick Z equal to a constant, right, where C just represents some real number, no matter what real number I pick, I always get something very similar for my level curve. It's not like some surfaces, depending on what Z value you pick, you get very different level curves, very different shapes for your level curves, right? Like say you have the top half of a sphere and you pick some Z values, you get a circle, some Z values, you get a point, one Z value, you get a point, and then most Z values, it's empty, right? But that's not the case for a plane, right? For a plane, as long as the plane isn't horizontal, then every Z value you pick, every constant you pick for Z, you always get a line, right? And not only do you get a line, you always get a line of the same slope, because if you solve this, what would you get? Write it in y equals mx plus b form, right? Do the algebra to write this in y equals mx plus b. What are you going to get? You're going to get negative fx ab over fy ab times y plus a big ugly constant, right? So this is the intercept, right? Oops, x. The intercept is a big ugly formula with all these involving all these constants. And I don't really need the intercept here, right? So I'm just going to leave it as that blue box. What I really care about is the slope, right? So that's the idea, is that the level curves of this plane, these are all lines of slope negative fx over fy, right? So when you draw if you draw the level curves, right, you have x, you have y, and then you have lines that all have the same slope, right? So this is These are the level curves of the tangent plane, right? So then the question is, if you're at some point, right? You're at some point AB, and you want to say, well, what direction should I go, right, to find the steepest rate of ascent, right? Imagine these, let's pick these to have some labels, right? So these are all going to be equally spaced with regards to their, if you pick equally spaced z values, right, they're all equally spaced level curves because it's a plane, right? It has a nice consistent rate of increase. So then what would you do if you want to increase as fast as possible? Imagine this is a topographical map of the terrain you're standing on, right? And imagine you're standing at point AB, at A comma B. Where should you go to increase as fast as possible? How would you walk uphill as quickly as possible? Well, what would you want to do? You'd want to go perpendicular to the level curves, right? That's going to be your direction of maximum increase, right? Because between two parallel lines, we're really using the distance between parallel lines, right? The between two parallel lines, the distance between them is going to be given by the line segment connecting them that's perpendicular to each of those lines, right? Um, that's going to be the shortest, the minimum distance between those two lines. So um, that direction right there is going to be the steepest rate of ascent. You're going to walk uphill as quickly as possible there, right? So the slope, which is here, let's say the direction of greatest ascent, right, is going to be what? It's going to be perpendicular to the slope of the level curves, right? And what is perpendicular? Perpendicular slope is negative reciprocal, right? So the slope that we should walk to find the direction of greatest descent is Fy divided by Fx, right? Now, if you wanted to express this as a vector, here it's just expressed as a number, right? But if you wanted to express it as a vector, you could, right? So what would you say? This is the rise and this is the run, right? So what is this? This should be your change in y and this should be your change in x, right? So now just express those if you want it as a vector quantity. It's what? It's partial x, partial y, which we have a nice shortcut for, right? We call it the gradient. So, right, because this is the change in the x component, and this is the change in the y component in order to get that slope, right? Okay, so there we go. There's our, that's the explanation of this theorem, right? Why this works, right? Why the gradient gives us our direction of steepest descent. So that's what we're showing here. So this would be what we were looking at there. That would be the gradient of this f. And one thing I should mention is here we're only really talking about the direction of the gradient and not the magnitude of the gradient. Right, you can have where the gradient is kind of gigantic, or you can have where the gradient is very small, right? But it will always be perpendicular to the level curve, regardless of the magnitude of the gradient. So, all right. So let's look at an example. Right, let's look at an actual example. So, for example, let's find the direction of steepest descent Let's do from the point 3 comma 4 on the surface 1 minus x squared minus y squared is equals 1 minus x squared minus y squared, right? So what is this surface? This surface, right, looks like x, y, and z. It has a y-intercept here at 1, at 0, 0, 1, right? And then it looks like a descending parabola along the x-axis, right? As well as a descending parabola along the y-axis. Right? And then the z cross sections are all disks. Right? So that's our surface. And then what do I have? I have this point 1, 2, 3, comma 1, 2, 3, 4. I have this point out here, right? This 3, comma 4. And then I want to go down to that point on the surface down here, right? And I want to find the direction of steepest ascent from that point, right? So I want to know what direction should I walk, this way? Should I walk this way, this way, this way? Which way should I walk in order to find the steepest uphill from if you were standing at that point on the surface, right? So it's going to be the gradient, right? Like we said by our argument before. So what's the gradient of this? It's going to be partial x of 1 minus x squared minus y squared, partial y of 1 minus x squared minus y squared. So it's going to be negative 2x, negative 2y. Right? That's our partial here, or both partials here, stacked together in a vector. That's what a gradient is, right? That's how we write down a gradient. And then what would this become? Notice the gradient, it's not just one value. The gradient is in general a function of x and y, right? It depends on x and y. So to get it at 3, 4, we plug in 3, 4, right? So we get, there we go. So I get negative 6, negative 8, right? All right. This from here is what? Negative 6, negative 8. It's going to take me to the origin and then through the origin by that same amount, right? So that's going to be the gradient at 3, 4 is negative 6, negative 8, right? So what does that tell me? It tells me the direction that I should walk, right? The direction that I should adjust the input in to find the rate of steepest descent. So it's saying, from this blue point, if you're going to take one step, whatever your step size is, right, and adjust the input to something new, you should adjust it to that point, and then you get to this new point on the surface to find the steepest possible uphill between the blue point and the red point. Right, that's what it's telling you. Now notice, once again, like I said, it might be tiny, it might be gigantic, but it's just telling you the direction of the steepest descent. Right, it's not actually telling you to take a step of that size to get the steepest uphill, right? If you actually took a step of that size, you end up on the same level curve, just on the other side of the mountain, right? So you actually haven't gone uphill at all if you from your net change in altitude is 0, right? If you took a step of size negative 6, negative 8. So it's just telling you the direction, right? You just walk a little bit in that direction. Not, but typically you think of it, then taking some very small step in that direction, right? And in fact, infinitesimal, right? But still, it's nice to because we're just talking about instantaneous rate of change. But it's still nice to imagine it as like taking some small step. So, all right. So there we go. There's our example. One follow-up to this. So note if you say so the direction in which the steepest descent occurs is the is given by the gradient, right? One nice follow-up property about the gradient is that the magnitude of the gradient um, then gives what that slope is, right? So that maximal slope, that maximal possible slope. So there's two things to say. There is saying one is saying in what direction should I take a step in order to get the steepest rate of ascent? But then you could say what is my rate of ascent when I do that, right? Well, the magnitude of the gradient gives you that steepest rate of ascent, right? Right, the max possible rate of increase. So that's why this is coming out so enormous, right? This -6, -8, because this paraboloid is really steep at that point, right? At that point 3, 4. That's why the gradient is so giant. So you have, what would the slope be? The slope at that point would be 10, right? So that would be the biggest rate of ascent, right? So that's one nice follow-up here. Also note if you want the steepest rate of descent, is in what direction? Well, just go backwards along the gradient, right? The negative gradient will give you the steepest rate of descent, right? Because then you'd have slope -10 going back down that way. Or in a more general setting, you could think of it here. Think of negative gradient is gonna, that's the direction that will let us descend through the level curves of the tangent plane as quickly as possible, right? Okay, so there we go. There's our brief introduction to gradients. We'll see them a lot more as we go throughout the semester, especially as we start looking at vector fields and potential functions and all that jazz. But all right, there we go. On to Lagrange.